Hi folks, welcome back. I've wanted to look at gradual typing for a while, and I think I've finally found the right paper to do it with. Now, gradual typing has become quite popular recently, especially with the rise of languages like TypeScript, and one can see why. Dynamically typed languages like JavaScript or Python are really popular. They offer programmers quick and easy way to do things, but as your program size grows, dynamically typed languages tend to yield code bases that are hard to maintain. And this is where gradual typing comes in, where you can still put type annotations on parts of your source code and then have it mix with the rest of your source code that might still be untyped. So you can get some of the advantages of typing without having to do the work of putting type annotations on all of your source code. The paper we're looking at today, first of all, enumerates the different ways in which one could implement gradual typing in a language, and then also does a survey of programmers to see how they feel about those various choices in the design space for gradual typing. Do they feel things are expected or unexpected? This work was done by folks at Brown and Northeastern University. The main contribution of this paper is to provide empirical evidence of how programmers judge gradual typing systems, whether they consider them to be intuitive or not. In most statically typed languages, we have the property that they are type sound. That's the whole point of typing. And what that means is, if you expect a value to be of a certain type, when you evaluate an expression of that type, you are guaranteed to get a value of the expected type. With gradual typing systems, however, we're mixing untyped code with typed code. And then the question becomes, what happens when a typed value flows into an untyped region of code, or vice versa? How should we interpret the types of a value as they flow across those boundaries? Take this simple example. Here we declare the type of this function to take a tuple of numbers and return a string. What should a gradually typed language do in such a scenario? What the authors have done is constructed a survey with examples like this, where values flow across typed and untyped boundaries, and asked users what behavior they would expect or what behavior they would like, and compared it with various options in the design space for gradual typing. With this, we can judge the preferences of programmers. In the survey, they ask two questions of each of the options presented. One question is how you feel about the behavior, whether you like it or not. And the other question is whether you think the behavior is expected or not. And together, this combination of feeling and expectation is what they call an attitude. Now, they claim that these two dimensions are roughly independent, in that you might find some sort of behavior unexpected but still like it because you're used to it. I personally went through the survey and almost always found that these two dimensions for me were the same, in that I liked behavior that was expected. Before we look at the results, let's look at a few of the survey questions to get a feel for what they were asking. Here we see in the first question, t is a tuple of two numbers, and then we declare x to be a single number and assign t to x. And then when we evaluate x, what should we expect? One option says that we should get an error on line 2 where the assignment is, and the type checker should say that we were expecting a single number but we got a tuple of numbers. That's what you would expect if types were fully enforced. Another option is that types are not enforced. This is what would happen if there was simply no typing annotations. X would simply be the same as the tuple. Here's another question. We have an array where the first element is a string and the second element is a number. And then we declare nums to be an array of numbers and assign t to it. So right away there's a type mismatch here because one of the elements of t is a string. And then we take first to be the first element of this nums array. And when we evaluate first, what should we get? One option is, this is the strongly typed option, is right on line 2 where we were assigning the array t to nums. It would complain about not getting an array of numbers because one of the elements was a string. Another option is you would let the assignment go through, but when you extract the first element, you emit a type error saying we got a string where we were expecting a number. So you're letting the assignment go through, but throwing a type error on extracting a value from the array. And the third option is, again, as if you had no types, you would simply evaluate the first element of the array. So I'd encourage you to go through some of the rest of these questions because they are quite illuminating in exposing how you feel about gradual typing systems. What is exactly the design space of these gradual typing systems? The authors break it down into 3 large categories, and they call these deep, erasure, and shallow. And let's look at each one of them in turn. Deep type systems will enforce types fully. Whenever there's an interaction between a typed and an untyped region, the types will be fully checked at runtime. They use this notation to say that an untyped value v is flowing into a context that expects it to be of type tau. And then they give examples of what would happen with the deep strategy. So if you have a value v that flows into a context that, for example, expects v to be an int, a deep strategy will check that v is an integer. If it flows into a context that expects v to be, for example, a tuple with the first element being tau 0 and the second element being of type tau 1, it will recursively check that the elements of v are of those particular types. And if v flows into a context where it is a function going from tau d to tau c, again, it will recursively check that the inputs and outputs have those correct values. So the deep strategy is essentially full type checking. You can expect that the statically declared types are enforced throughout, even when they flow into untyped regions of code. The next strategy is erasure, which totally ignores types. The erasure strategy does allow you to annotate your code with static types, but those are useful only when you're coding. When the code is running, those types are simply erased. So compared with the deep strategy, when a value flows into a context expecting a specific type, nothing is checked. Now, erasure is a strategy employed by TypeScript, which is by far the most commonly used gradually typed language today. And it's completely unsound because it doesn't check any of its types. So why is this strategy so popular? The big reason is that you can use these type annotations at coding time. You can find out type errors when you're actually coding in an IDE. You can get things like autocomplete and refactoring with types. In terms of implementation, this is of course the simplest to implement. The semantics are exactly the same as that of the host language. So the semantics of TypeScript are exactly the same as that of JavaScript. Every JavaScript program is a valid TypeScript program. And what this means is that it runs as fast as the original language. And then we come to the third strategy, which they call shallow. And shallow is midway between the extremes of deep and erasure. It basically checks that values have the right shape, not necessarily the right type. So if a value goes into a context expecting an integer, you do check that it's an integer. But if there's a more complex type like a tuple or a function, this strategy doesn't go and check the exact types, but just checks the shape. For a tuple, it wouldn't check the types of the individual elements of the tuple, but just that the value is a tuple. For functions, this strategy would not check the exact types of the input and output of the function, but just that the value is a function. Let's look at what they found in their survey results. One big area of consensus was that the erasure strategy is disliked and unexpected, whereas the deep strategy is both liked and expected. This shows up, for example, in that first code snippet we saw, where we were trying to assign a tuple of numbers to a variable that was expecting just one number. And you can see here that deep is overwhelmingly liked and expected, whereas erasure is overwhelmingly disliked and unexpected. We can see that same preference in a more complex example as well, where we have an object where one of the fields is a function that expects a number, and most programmers expect this line number 3, to throw an error because t is a string and we're trying to pass a string into a function that expects a number. There are a number of other factors to consider, such as whether the programmers prefer using typed languages or dynamically typed languages, how much exposure they've had to languages like TypeScript, and so on. And I encourage you to read the full paper for those details. So to conclude, what does this survey tell us about language design with gradually typed systems? The big takeaway is that the erasure strategy is surprising and unintuitive. Most developers do not expect these type annotations to be completely ignored at runtime. Developers have the expectation that a gradual typing system should remember the type associated with the value even when it flows to an untyped context. So that was a look at a very broad classification of gradually typed programming languages and what programmers feel about various points in the design space for gradual typing. I hope you enjoyed that, and I will see you next time. Thank you very much.